Hi, welcome back to 0x41414141. In this video I'm gonna show you how to solve a Crackme using Cadre and Z3. Cadre is a cross-platform Qt graphical user interface written in C++ for Radare 2. I'm gonna use it for the reverse engineering part. I'm gonna use Microsoft's theorem prover Z3 to generate a valid key. You can download the Crackme from this mirror of crackmes.de. The password for the archive is crackmes.de. And let's open it with Cadre. We use the default analysis settings. Let me close some windows that we don't need at the moment. So we have a 32-bit binary, not stripped. Let's check for interesting strings. Here are three strings that give some hints on how the program works. It expects a serial and it checks if it is correct or not. Let's jump into main. I zoom out to have an overview of the program's structure. On the left we can see this pattern that looks like a series of checks. These probably are the paths taken when the check fails. While on the right we have a loop. Let's go back to the start of main. As you can see, argc and argv are not automatically named, so we do that using Shift N. Then we rename the strings pointers to bad and good. argc is then compared with the 1, so we need at least one argument, otherwise the usage is printed. So we need at least one argument, that will be our key. We add a comment with the shift column. Our key will be then pushed on the stack. We see that we take RV, we add 4 to get the pointer to our string, and we call string length. So the key must be 10 characters, 10 bytes. Otherwise you can see that bad message is printed. Let's go on. Now again a pointer to argv is moved into AX, then 4 is added, so now it points to our string. Then a variable is moved into EDX. If we go back using ask key, we can see that it was previously initialized to 0, and it is later added to EAX, which is used then as a pointer to a byte. So this means that local 10h is used as an index inside our string. So we can name it I. The loop goes on until a null byte is found. So if the character is not null, we check if it is inside the range that goes from 96 to 122. And if we are inside this range, argv is moved into EDX, 4 is added, so now it points to our string. Then the current index is moved into EAX. The pointer from EDX is copied into ECX, and EAX added to ECX. So now ECX points to the current character. Then we move again argv in EDX, we point to our string, We extract the current character, we copy it into AL, and then we subtract 32. So what this loop does is subtracting 32 from characters that are inside that range, and then simply EAX is incremented and the loop goes on. When we break out of the loop, we move into the left part of our graph where the checks are taking place. So let's see the first check. As usual, EAX is set to point to our string. Then the first character of our string is copied with sign extension into EDX. We then again set EAX to our string. We add EAX9 and we extract the current character, so the one with the index 9, into EAX with sign extension. At this point, we subtract 3 from EAX and then we compare EDX with EAX. This is equivalent to this constraint on our key. And if we now move to the following check, we can see that we have the same structure with just different numbers and an addition rather than a subtraction. So we can just change the previous comment. Same goes for the following one. And yet another one. We are now arrived to the final check, which is slightly different from the previous one. In this check, we begin as usual setting EAX to point to our string. Then we extract with the sign extension the character with index 4, and we store it into EDX. Then we do the same with character with index equals to 5, and we store it into EAX. We then add these two. Then we have a division which was optimized by the compiler, but what this actually does is dividing our sum by 2, and then this is compared with the first character of our string. So this is equivalent to this constraint. After this final check, a variable is set to 0 or 1, whether we pass the checks or not. And if this variable was set to 1, the good message is printed, otherwise we get the wrong message. So let's have a brief recap. We need at least one argument. It should be a string of 10 characters, and then the characters inside a certain range will be reduced by 32. We then perform some checks on the resulting string, and if they are satisfied, we return a success message. So let's now write a Python script to solve these constraints. I'm gonna use the Python API for Z3. So we create a solver and an empty list. We then iterate over 10 characters. For each character, we create two variables, which are bit vectors, which are symbolic variables used by Z3. We name v the first 10 and v underscore the second 10. Then we add the constraint for the current character, and essentially it can be inside the range or not. If it is inside the range, so if v underscore is greater than 96, v underscore is less than or equal 122, then v will be equal to v underscore minus 32. Otherwise, if you're not in the range, and this can happen if v underscore is less than or equal to 96 and v underscore is greater than 122. In that case, v will be equal to v underscore. Then we have to add constraints to avoid bad characters, which are spaces, new lines, carriage returns, null bytes. Then we insert our symbolic variables in a list. And finally, we add the constraints that we have in the checks. We can simply copy the comments. At this point, if there is at least a solution for our model, we're gonna print it. So first, we have to create a list from our model. We convert it to its string representation. We strip the leading and ending brackets. Then we split at this separator. And then we want to sort all this. So underscore variables will be the second half of the vector. Now we use map to apply an action on every item in this list, which is we want to write on standard output a character, which is the current item, split it, equals. So we extract the value of the variable, we convert it to an integer, and we apply everything to hell. Let's try it, make it executable, run it. Okay, let's check with XXD if this makes sense. And it works.